These notes are on Chapter 7, Section 2 on similar polygons. So just to quickly review, what does it mean when two segments are congruent? So congruent means equal, so the segments have equal length. What does it mean when two angles are congruent? Again, congruent means equal, so their measures are equal. So we will be, even though we're talking about similar figures, in similar polygons, angles will be congruent. So to go over the vocabulary, similar means similar, they're alike but not identical. So they have the same shape but not necessarily the same size. So the two squares at the right are similar because they are the same shape. Okay. And how are they not similar? They're not the same size. A key concept for similar polygons is something we've done already for congruent triangles. Two polygons are similar if their corresponding angles are congruent and the lengths of the corresponding sides are proportional. So angles must be congruent, sides are proportional. So if we are matching up the corresponding angles, angle A corresponds to angle G, angle B corresponds to angle H, angle C corresponds to angle I, and angle D would correspond to angle J. So remember, you can use the letters in the name of a polygon to help you organize your corresponding angles and sides. So an extended proportion means we're comparing more than two ratios. So we're going to compare corresponding sides. So side AB and GH. Side BC would go with HI. IJ are the last two letters, and that would correspond to CD. And then AD corresponds to GJ. So this would just be a review of what we did back in Chapter 4. So to understand if polygons are similar, we look for two things. First of all, you want your angles to be congruent. So again, look at the names of the polygons, especially if you don't have a picture. So D would correspond with angle H, E would correspond with J, K would correspond with F, and L would correspond with G. And again, in the extended proportion, DE, HJ, EF, JK, KL, FG, and the last would be DG and HL. So if you had actual side lengths, we would check and make sure all of those ratios were equal. A key word here is scale factor. A scale factor is the ratio of the lengths of corresponding sides of similar triangles. So when we determine similarity, you want to make sure you match up corresponding sides. So if we circle the short sides of each rectangle, first of all, if we look at KL, that's a short side. NM, or MN, is a short side. WZ, and XY. And then the long sides would be the four remaining pairs. So you want to make sure when you're doing ratios that you compare corresponding parts. So in this figure, we're going to write the ratios of corresponding sides in simplest form. So when we started with KL, that would correspond to XY. Think of this rectangle as turned, so short side matches with short side, 10 to 15. You can reduce this by dividing by 5, greatest common factor, reduces to 2/3. LM corresponds to YZ. So LM would be 15. YZ, since this is a rectangle, is the same as its opposite side, which would be 20. And again, you want to reduce to lowest possible terms. So if we divide by 5, you get 3 over 4. In this we compare mn to zw, and again wz would be 15, kl would be 10, and we have that same ratio, that would be 2 to 3. And then nk and wx would be 15 over 20, which reduces to 3/4. So you can see that we have two different ratios. So since all the sides are not proportional, these two rectangles are not similar. So since they're not similar, we don't write a similarity statement. So these two polygons, the scale factor was 2 to 3 only for the short sides, so that was not correct. If we compared the long sides, the scale factor was 3 to 4, so the correct answer is the polygons are not similar. So we can use proportions such as this to decide for missing side lengths. So first of all, you want to make sure that you choose correct corresponding sides. So if we're looking at side EF, we're looking for the side that corresponds to it, which would be AB. So since corresponding sides of similar polygons are proportional, we want to write out the correct name here, which would be A to B. Then we can substitute. So in place of AB, we put 5. And then the cross products property, you multiply 9 times y. 6 times 5 is 30. Divide each side by 9. And you can get a fraction or a decimal, so this would be 3 1/3. So the length of side y is 3 1/3, or if you want to leave it as an improper fraction, it would be 10/3. Here we'll use this to solve perhaps a real-life problem. So you have a rectangular poster 6 inches high by 10 inches wide. What are the dimensions of the largest complete poster that would fit in a space 3 feet high by 4 feet wide? So first of all, you want to make sure that you change feet to inches. So 3 feet would equal 36 inches. So take 36 inches, divide by 6, because we're comparing height here to width. And then for the width, 4 feet would equal 48 inches. So 48 divided by 10 is 4.8. So you can't enlarge it more than what would be the smallest possible scale factor. So you can enlarge it at most 4.8 times. So if x is our new height of the poster, we'll write a proportion and we'll solve for x. So when we want to write the proportion, we'll take the original size, 6 inches high by 10 inches wide. We don't know quite how high we can make it, but we know the maximum we can expand the width is to 48 inches. So when you cross multiply, 6 times 48 would equal 10 times x. 288 equals 10x. So if you wanted to enlarge it to the absolute maximum, the largest complete poster that would fit would be 28.8 inches by 48 inches. And that would fit into the space. Okay, our final example is using a scale drawing, which is really what you do more of in real life, depending on what profession you'd like to go into. So we're going to use the scale drawing of a bridge and what would be the actual height of the towers above the roadway. So let's say we used a centimeter ruler to measure the height of the towers above the roadway in the scale drawing. So we measured from here to here, and we got 1.5 centimeters. So we're going to let h be the height of the towers above the roadway. So the tower height in the drawing and the actual height and the scale is 1 to 200. So we have 1 to 200 would equal 1.5 over h. So when we cross multiply, you get 1h equals 200 times 1.5. When you multiply that, you get h equals 300. So the actual height of the towers above the roadway would be 300 meters. So let's do a quick check of what we learned. So if the triangles at the right are similar, 3 similarity statements for the triangles. So first of all, we do this like we did with congruent triangles. The order matters. So let's say this larger triangle we'll call ABS. Look for corresponding angles. So A corresponds to P, B corresponds to R. So we'd name the second triangle PRS. So A corresponds to P, angle B corresponds to angle R, and angle S corresponds to itself. So triangle ABS would be similar to PRS. If we switch the order of the letters, BSA would be similar to RSP, and SAB would be similar to SPR. So the similarity statement, you'll notice, does not have the equal symbol underneath the similarity. And that is the notes for similar polygons.